Welcome everyone, and welcome to Bird Math. In this video, we're going to be talking about the following limit, and that's the limit of the function sine x over x as x approaches 0. There are numerous ways to evaluate this limit, and typically with any limit, the first thing that you want to do is just try a direct substitution. So when we do that, when we just plug in 0 for x, we get sine of 0 over 0, which is 0 over 0, an indeterminate form. So that's not going to work. Another option we have is to simply graph it in graphing software, but let's assume we don't have that option. Another option is to use L'Hopital's rule. But another way, and the way I'm going to show you today in this video, is to use the Squeeze Theorem. Now notice what we have here. We have a unit circle, and the unit circle is simply a circle of radius 1 centered on the xy plane. So what that means is every radius is 1. So the line AB is 1. The line AD is 1. And I'm going to write the following statement, which should be obvious. I'm going to say that the area of triangle ABD is less than or equal to the area of sector ABD, and that's less than the area of triangle ACD. And this should be obvious. If you look at the area of triangle ABD, which is this triangle right here, it should be obvious that that is less than the area of this sector ABD. And it should be obvious that that sector is less than the area of this triangle ACD. So it should be apparent that this statement here is true. And so we're going to use this statement to prove the sine x over x limit. So to start, the area of any triangle is simply half the base times the height. The area of any sector is simply theta, and sector is simply a slice of a circle. It's a piece of pi of a circle. So it's simply the ratio, the theta, over the whole circle times the area of the circle. So theta over 2 pi times pi r squared. And that's less than or equal to the area of the triangle ACD, which, again, formula is just half the base times the height. Okay, so for our first circle, ABD, let's fill in these formulas. Let's fill in these variables. ABD, triangle ABD, the base of triangle ABD is the line AD. And the height of triangle ABD is the line BE. You'll notice here in the sector formula that these pi's cancel out. So we're left with theta over 2 times r squared. Well, you'll notice that r of the sector is simply 1. This is a unit circle. So we could just plug in 1 there. And for the final triangle, ACD, you'll notice the base is this line AD, and the height is this line DC. Now, here in our first triangle, we have 1/2 times line AD times line BE. Well, line AD is also just the radius of the unit circle. That's 1. Now, line BE, we don't know. So we're going to have to think a little bit how to figure out what line BE is. If you remember from trig class, sine of theta is the opposite over the hypotenuse. So in this case, here's theta. The opposite is line BE. over, and of this triangle right here, triangle ABE is what we're looking at, by the way. And we're looking at triangle ABE in order just to figure out the height, this line segment BE. So if we look at this triangle ABE, the opposite of theta is the line BE, and the hypotenuse, well, that's just the radius again, that's just 1. So it's just BE over 1, which is just BE. And so this line segment BE is simply sine theta. You'll notice here for this triangle ACD that the base line AD is also just the radius, it's just 1. And the height is this line segment CD, and we don't know that. So we have to think a little bit more how to figure this out. And you might remember that tangent theta is the opposite over the adjacent. Well, in this case, tangent theta is the opposite line segment CD over the adjacent line segment AD. We already know what that is. That's 1. And so CD over 1 is just line CD. And so the length of this segment CD is simply tangent theta. And we could just plug that in here. And by the way, just so I don't confuse you, I called it line segment DC here, but up there I called it line segment CD. They mean the same thing, but we'll keep it consistent. We'll call it line segment CD. Okay, so now let's clean up this inequality a little bit. 1/2 times 1 is 1/2. Looks like we get sine theta over 2 less than or equal to theta over 2 times 1 squared is just theta over 2 less than or equal to 1/2 times 1 squared. I'm sorry, not 1 squared, but it doesn't matter. 1 squared or 1, they're all 1. So this is just tangent of theta over 2. Now we're going to manipulate this a little bit. So we'll multiply every term here by 2, and this will cancel out all the denominators. So we have sine theta is less than or equal to theta, which is less than or equal to tangent theta. You might remember that tangent theta is nothing more than sine of theta over cosine theta. And we're going to do some more manipulation here. I'm going to multiply every term in this inequality by 1 over sine theta. So I multiply here, I get sine theta over sine theta. Then here I get theta over sine theta. And here I get sine over cosine times sine times 1 over sine. The sines cancel out. I'm left with 1 over cosine theta. You may notice that sine theta over sine theta cancels out and becomes 1. And then I'm going to raise every term to the -1 power, which is just taking the reciprocal. So the reciprocal of 1 is still 1. The reciprocal of theta over sine theta is sine theta over theta, and you may see where we're going with this now. And the reciprocal of 1 over cosine theta is just cosine theta. Now, at this point, I'm going to use a property of limits, which is that you can distribute a limit across the inequality. So if I have this statement, 1 is less than sine theta over theta, which is less than cosine theta, then the next statement is also true. I can take the limit of each term as theta goes to 0. Well, the limit of 1 as theta goes to 0, just a property of limits of any constant, is just that constant. So it's just 1. I'm going to leave the middle alone. And the limit of cosine theta as theta goes to 0, well, we could just evaluate this, just plug in 0 for 1. And we get cosine of 0 is just 1. And so you will now notice that the limit as theta goes to 0 of sine theta over theta is greater or equal to 1, but it's also less than or equal to 1. So this limit is being squeezed on both sides by 1. And so the only thing that this limit can be, the only value that it can be, is 1. And in this case, we use theta, but we could just flip our variables. And so we've now proved that the limit of sine x over x as x approaches 0 is 1. And just to further reinforce that, we know when we direct substitute 0 into for x, we get 0 over 0 in indeterminate form. That allows us to use L'Hopital's rule. So if we have a quotient, which we do, we take the derivative of the numerator over the derivative of the denominator, and then evaluate the limit. So this is the limit as x approaches 0 of derivative of sine is cosine of x, and the derivative of x is just 1. Now we can direct substitute x in for 0. We get cosine of 0, which is 1 over 1, which is just 1. And that checks out to what we found over here. And I think that's pretty cool, and I think it's pretty easy to follow the logic of it. And I hope that made sense. I hope that allows you to know what the squeeze theorem is and how to use it. And I appreciate you guys watching Bird Math. I'm going to post some more videos, and thanks for watching. Bye.